Welcome to NPTEL course on power system protection. We are continuing with the modules on network protection with renewables. In this lecture, we will address the protection challenges specifically to distribution systems. In last lecture, we have seen that renewables in the form of photovoltaic, wind and others, they are being integrated to the network using inverters and transformer arrangements, and in that such situations they contribute current and voltage differently than the conventional synchronous machine based sources, and that makes the big difference in the fault characteristics of such distributed energy resources. Let us come to some few challenges which I like to see in this lecture related to distribution system. First one is on protection blending. So, this is a distribution system 11 kV 50 Hz system, and it is this feeder you can say that runs to meet the certain load. A fault happens to be there at point F here with certain resistance RF. Let us, this is a three phase fault situation. So, therefore, this relay will see certain amount of current based on the associated fault impedance and the RF. Typically, for three phase fault, RF is much smaller. Now, we have considered here the source to be pretty strong. So, as compared to these impedances, source impedance is much smaller. So, for this case, three phase fault case, the corresponding IS becomes equals to voltage here upon the corresponding impedance of this path ZL dash plus RF. So, let us say for this case, the system simulation reveals 884 ampere. Now, we include in the system a PV connected, you can say that just beyond the fault position. So, this PV, let us say a capacity of 5 megawatt, and now for this fault the grid provides as usual fault current, and so also the PV considered provides fault current, and combinedly they are having two currents contributed by the two sources. So, that means that to this fault the total current will increase. So, that current is IS from the grid side and IPV from the photovoltaic 5 megawatt photovoltaic. Now, what happens? We like to analyze. So, this can be analyzed considering each source. So, superposition theorem we can apply, and let us say first our conventional grid side. So, the grid side you can say that path we have already analyzed in the earlier slide. So, that becomes equals to, let us say we have designated in such situation IS dash equals to Vs upon Zs dash plus Rf, same fault point. Now, the other part that the PV system which happens to be a current source. So, the current source you can say that in this case the current source remains open. So, that path is not shown in this case. Now, with this current source you can say that IPV will supply to consider to this fault, and this side you can say that will be shorted, you can say that here considering the 11 kV source to be small impedance, negligible impedance. So, that reveals you can ZS part and the RF path. So, therefore, the corresponding IS double dash in this path will be equals to RF upon ZL dash plus RF into IPV. So, this is the current you can say that flowing through this path, and the rest of the current you can say that will flow through this RF. Now, what you see is that the using the superposition principle, the IS, note the IS is the current flowing through the relay. So, that relay current becomes equals to, you can say that IS dash contributed by source grid source minus I s double dash contributed by, because the I s double dash is flowing in the reverse side, then to the I s dash. So, minus I s double dash. So, this you can say that becomes equals to V s upon Z L dash plus R f minus R f upon Z L dash plus R f into I P V. So, that what we see that this part is nothing but the current which we see in the earlier slide only contributed by this grid source, grid as the source, and this part you can say that is contributed by the I P V. Now, this total current is flowing through this relay which is at the substation. So, that means that this you can say that relay will see a less amount of current for the same fault position, same RF, everything remaining same in the presence of PV as compared to the without the presence of PV. So, that is found to be 745 ampere as compared to you can say that the 884 ampere you can say that when the system does not have the photovoltaic plant. So, what you see that these a factor of this with the contribution of the IPV, when the PV is connected you can say that beyond the fault point in this arrangement, then there is a you can say that observation that the substation relay current decreases. So, that we say that the IS, the current seen by the relay with PV becomes less than without PV. Further you can say that the more is the PV capacity, more will be current from the PV, IPV will be more and more, and with IPV more, this negation part, negative part becomes more, and therefore, you can say that the decrement in current becomes more and more. So, what we say here that we see that in case of smaller current in the identity curve, smaller current means the corresponding time taken will be more and more. When a synchronous or inverter based DER is present between the main substation and any fault, as we discuss here, fault current contribution from the upstream grid is decreased. That is what we say that the relay will see now decreased amount of current, sensitivity of the relay decreases. This undesirable effect is called the blinding. This undesirable effect is called the blinding, and that will you can say that delayed the decision process of this relay. Furthermore, going into the distribution system issue with renewable resource. So, we will see how the overcurrent relay, existing overcurrent relay will perform in case of presence of any DER like PV or so. Now, let us have a system having 3 buses, and we have you can say that the corresponding fault at F, and we have 2 relays here R1 and R2. These R1 and R2 are being having CT ratio 150:5, 100:5, pickup current let us say both are having 10 ampere. We have learned this you can say that in the overcurrent relay principal coordination earlier in the lectures. The R2 the farthest relay you can say that will have the smallest you can say that time multiplier setting. So, that you can say that TMS 0.1 that belongs to this R2, and let us say as per the setting we have TMS 0.2 you can say that for the R1 for this distribution system with having different loads and all these things clearly mentioned here. Now, we say for this fault the IRN, IR1 and IR2 will be equals to ES upon the impedance up to the fault point. So, that will be ZS, ZAB and ZBF. So, that is what we say. Let us say this is a 3 phase fault case. Now, what will happen? PV is connected at bus B. So, 5 megawatt PV connected at bus B, same fault. Now, with PV connections, the fault current seen by relay R1 decreases. We have already mentioned you can say that with PV you can say that connected you can say that in case of here the corresponding you can say that the contribution of this R1 will be consider that will be decreasing, resulting in delay in relay operation of what this R1. But for R2 what happens, we see here the amount of fault current for this fault will be contributed from this side, from this source and as well as this source. So, the amount of current increases, you can say that, by that relay. So, that you can say that is from these relations, and resulting in that we see that you can say that from this curve you can say that the relay R1 you can say that sees less amount of current and relay R2 you can say that sees larger amount of current. So, therefore, you can say that we see that the corresponding you can say that R2 decision time decreases from 0.14 to 0.12 and R1 decision time increases from 0.4 to 0.55. Note that for this fault R2 is the primary relay and R1 is the backup relay. What you observe that you can say that the backup relay decision is being delayed. So, the consequence of overcurrent relay is that in that kind of things it results in delayed backup situation. Next issue is on the, there may be issues you can say that on the coordination of the coordination issue in the overcurrent relay. See a system like this, we have multiple buses here in the distribution system, and we like to have coordination between relay R2 and R3, the last you can say that two relays in the system perspective, with you can say that the PV connected being at bus P. So, what happens that the corresponding for these coordinations we have you can say that maximum fault current what R3 sees, that is the basis for the coordination between R3 and R2, because R2 will protect also line you can say that section CD as a backup, primary being the R3 relays. For this case the corresponding IR2 equals to, for this fault at this bus equals to ES upon ZS plus ZAB plus ZBC and contributed by PV equals to ZS plus ZAB plus and upon you can say that ZS plus ZAB plus ZBC. Now, this current you can say that will be considered also through this R3 relay. So, IR3 equals to IR2 for this case. Now, what will happen in this case that the between R2 and R3. So, we have you can say that R3 you can say that relay the lower curve and R2 you can say that relay the upper curve in terms of the coordination business. So, earlier when PV was not there, then the coordination was being carried out you can say that at the these positions. So, therefore, you can say we have a coordination here, and this coordination was meeting our coordination time of 0.2 to 0.3 second as usual. Now, what happens with the PV, the corresponding fault level of current increases, and therefore, you can say that it shifts to this right, and that leads to you can say that if you see the nature of the curve by IDMT, then the coordination time which is available becomes this. Now, note that this coordination time is smaller than you can say that this you can say that time you can say that what we see in an IDMT curve, we have learned this in OCR coordination. So, this coordination time may be smaller than 0.2 second or so, and that may not be adequate you can say that may be insufficient, and that is a challenge you can say that in case of such a scenario. Note that with the capacity increment of the you can say that the PV more and more, the corresponding current level increases. So, therefore, you can say that in the IDMT course again it shifts towards the right, and that may degrade the corresponding coordination further more also. Now, we have also discussed the in case of overcurrent principle also the fuse saving scheme. So, what happens in the fuse saving scheme is that in case of a downstream, in case of a downstream transient fault, most of the faults are transient in nature in overall line. In case of a downstream transient fault, what happens that that this fuse you can say that is not allowed to be blown out initially. So, for that reason you can say that in the upstream region you can say that the corresponding relay you can say that has an instantaneous the corresponding upstream relay has an instantaneous protection and also an IDMT characteristics. The instantaneous relays operate first to making a judgment that assuming considering that you can say that the fault is transient in nature, and then you can say that it reverts back to you can say that to the normal you can say that IDMT characteristics. By that way you can say that the fuse can be saved for most of the consider transient faults, and therefore, you can say that the restoration time becomes less and there is no need to go for people to go for replacement of the fuse. So, that is why you can say that the principle of fuse saving scheme. Now, what happens with DR connected beyond this, you can say that this line, then what happens that this you can say that distributed energy resource PV or wind or so, for this you can say that fault in this downstream, the corresponding contribution you can say that of the DR will also there. So, within that you can say that transient period, the level of you can say that fault current becomes more, and who knows the corresponding fuse may be blown out within that, even for that same you can say that transient faults also, and that is what you can say that the fuse saving scheme you can say that is being under scrutiny in that situation also. Let us come to an example in this situation. So, here you can say that we have that fuse here, fault happens to be here, and then fault current is contributed from this side and also from this side, this 11 kV system and so. Now, what happens you can say that we have a fuse characteristics that is in the blue, we have instantaneous protection first one. Now, we have learned in our you can say that fuse saving schemes that this instantaneous you can say that protection that should act faster than the fuse, then only you can say that the fuse can be saved for this fault. So, therefore, we say you can say here that the decision time by the you can say that the operating time of the relay must we can say that smaller than the you can say that by the fuse time, and that must be there. Now, note what happens in this case you can say that with you can say that the PV connection becomes more, with the PV penetration becomes more, then the current through this you can say that path voltage path becomes more, and then you can say that the current being more you can say that the it goes to this for this IDMT characteristic of this fuse, almost the IDMT characteristic of the fuse, it goes to the higher current, and this higher current leads to you can say that a point like this, where this you can say that current may lead to a situation the fuse you can say that current the fuse you can say that blown out period may be smaller than the instantaneous protective relay characteristics, and that is what we see here. Without PV connections, it was leading to 800 ampere melting time of the fuse. With PV connection, you can say that the corresponding current becomes 1100 ampere, and that is why I can say that the situation here, and that leads to a situation that the fuse may be blown out before the instantaneous operation, and in that case you can say that the corresponding fuse saving scheme is under scrutiny, it may not operate you can say that as expected. What you see from these situations is that in that situations that these such kind of you can say that schemes you can say that are under scrutiny with renewable integration in these systems. So, we have to see whether the functionality of such schemes you can say that will be correct or not correct you can say that with the higher and higher level of penetration of renewable resources. Now, going to another issue on sectional ledger. So, we have you can say that as already mentioned for the earlier classes, we know sectional ledger I can say that and reclosure they have a coordination. So, the sectional ledger you can say that it's connected to you can say that a downstream feeder with the probability of having more number of you can say that faults in that one like a rural feeder also, and that may not hamper to a critical loads like the hospital load or any important load and so. So, in that situation this sectional ledger you can say that helps in that way. So, what it does you can say that in terms of that if a downstream fault happens to be there, the reclosure you can say that assumes it is a temporary fault and the reclosure operates multiple times 2 or 3 depending upon as per the setting. Now, these you can say that for a fault here the sectional ledger counts the number of interruption by the reclosure, and if it finds the corresponding current to be high in this path, then while the reclosure has opened at some time, the sectional ledger opens you can say that, and I am say that clears the fault, thereby I can say that the other you can say that sections in the distribution system restore the supply very quickly. This helps in you can say that in reliability of the systems, and that is what you can say is being used. Now, what we see here with the DER connected in this situation. So, what will happen that for this you can say that for this you can say that fault, you can say that permanent fault in this you can say that section, the corresponding fault current flows to this path continuously, and the reclosure side you can say current flows here. So, even though the reclosure is open, this current flows. So, therefore, sectionalizer will not be able to see you can say that the interruption of current. It means that the number of counts upon which the sectionalizer decides will be now will be a different one, and that is why we talk about the miscount by the sectionalizer. Once again, that the sectionalizer counts the number of interruptions by the reclosure, but from the current contributed by this PV will not allow interruption of current to the sectionalizer. So, therefore, you can say that the number of counts by the sectionalizer will be not correct, as we can say that it was being designed for without consideration of the PV. So, that will lead to you can say that sectionalizer operation also you can say that improper in such a situation. That is you can say that is the challenge. So, as I already mentioned for earlier issues of you can say that related to renewable resources or DERs. So, we have to verify for a systems before more and more you can say that renewable being integrated in these systems on the sectionalizer performance also. Now, one other issue you can say that we say you can say that these are 33 kV systems, we have further ground downstream you can say that 11 kV systems, 400 volt systems, LT system and so. Now, see here you can say that what is the protection solution in that kind of perspective. One literature suggests you can say that suppose you have you can say that take distribution you can say that system you can say that having renewable resources DER and then load connected at this 11 kV system also some 5 megawatt or so, and then at this bus you can say that we are observing at C bus what is the corresponding relay performance for this breaker. Now, what happens that there are multiple options here. One is that the overcurrent relay, but we know that the DER you can say that will not able to pass on large amount of current. So, overcurrent relay is under scrutiny. So, overcurrent relay is under scrutiny, but this you can say that the relay associated with this you can say that breaker. Now, there is another option you can say that whenever a fault happens to be there in this you can say that line, then we expect that the voltage of this bus will be down. So, we are talking about under voltage you can say that issue, but if this line becomes longer and a fault happens to be towards the close you can say that the PCC bus or the bus B, then you can say that this degrade in voltage or lowering of voltage will be not significant, and the under voltage relay here may not be able to pick up. So, then you can say that neither you can say that overcurrent or under voltage you can say that finds the proper fault you can say in this line also in such a scenario. So, in that kind of things the different you can say that perspective you can say that is being done, and that is you can say that is called voltage resistance overcurrent relay used for different application perspective, but here it can be applied in terms of that 51 VR. So, in this case the corresponding current becomes an adaptive one. So, depending upon the terminal voltage that is at the bus C, the corresponding pickup current you can say that depends upon the level of voltage. So, whenever a fault happens to be here, the voltage here may go down, and note that the corresponding DER feeds the corresponding load and the excess amount of current flows towards the fault, and depending upon you can say that the corresponding voltage dip and all these things. So, see normally what happens that suppose there is no load, then this corresponding DER will feed all currents to this side PCC side. So, that you can say this is normal functioning, 100% you can say that current will be seen by the relay you can say that even at the normal rated voltage also. So, that is a normal situation also. So, whenever a fault happens to be there and the load is being fed by the DER, then the corresponding fault current flowing through this path may be substantially low, and that is we can say that we talk about that with the lower voltage you can say that the corresponding pickup current setting is being lowered in that perspective. So, this is about the trip region in this case, and this is about the block region in this perspective and all these things, and that the term as voltage resistance overcurrent relay principle can be applied in case of such environment. But the problem you can say that such you can say that such an approach has issue of you can say that coordination issues and all these things. So, at multiple places if we apply this you can say that becomes a challenging. So, what we try to figure out here is that there are related solutions, but there may be partial, it may not be a complete solutions to the perspective, because DER with inverter you can say that interface may not provide you can say that significant current. So, over current relay is under scrutiny, and different perspective of over current relay challenges we observed in the earlier slides. And also under voltage relay you can say that performance may be limited. So, then we have to, then the whole protection scheme of the distribution systems with higher and higher level of penetration is under scrutiny. Now, the others you can say that schemes which is evolving you can say that in these kind of things about the with the concept of macro grid, which can be also extended to you can say that to the distribution system also, is on the perspective of you can say that communication assisted you can say that relay communications assisted protection schemes, where we have a centralized you can say that protection schemes, and you can collect data from you can say that different IDs of the systems. Now, what is the benefit of this? When a fault occurs in the systems, the protection and control devices or the IDs you can say that in the systems at multiple locations in the systems, they observe you can say that the corresponding fault situations, and in particular you can say that the ID is near to the fault, they sense you can say that currents and voltage changes, and with the centralized fault detection mechanism, these you can say that information from such IDs you can say that will be you can say that process, and then you can say that we can infer the particular you can say that fault section in the system where the fault has occurred, and then a command can be issued to open the particular breakers, thereby the selectivity sensitivity of the systems can be improved. And also you can say that the restoration of the you can say that system can be quicker if you know the exact section and the location of the fault from the information collected from different IDs. So, in general we say that the distribution system network protection schemes are being affected by the presence of these the DERs, the inverter interface you can say that generators, sources, proper coordination, reclosure actions, fuse you can say that performance, fuse saving methods, all form of you can say that overcurrent principles are under scrutiny. Presence of DERs needs special attentions as regard to the distribution system protections, and in particular with more and more you can say that DERs being integrated into the systems, level of penetration increasing day by day, the protection schemes are under scrutiny, and they have to look into, and alternative solutions may be required in that perspective. Thank you.